When Voyager 1 crossed the boundary of our entire solar system back in 2012, scientists couldn't actually watch it happen. Not because nobody was paying attention, because the one instrument specifically designed to directly measure that exact crossing had already stopped working years earlier, leaving researchers to reconstruct one of the most significant moments in the history of space exploration entirely after the fact, piecing it together indirectly from second-hand evidence. 6 years later, when Voyager 1's twin, Voyager 2, approached that same boundary, it carried something its sibling no longer had. A functioning instrument still gathering data in real time, giving scientists their first, and to this day only, direct live measurement of what actually happens at the true edge of our solar system. This is the real story of the one specific advantage Voyager 2 had over Voyager 1, and what that advantage let scientists actually witness for the very first time. Every detail in this video is drawn directly from NASA's own published mission records and statements from the scientists who actually led this research. Not speculation, not exaggeration, just a genuinely underappreciated piece of how we actually came to understand the true edge of our solar system. Let's start with what that instrument actually is, and why its failure aboard Voyager 1 mattered so much. Both Voyager spacecraft carry an instrument called the Plasma Science Experiment, sometimes shortened to PLS, specifically designed to directly measure the properties of plasma. The ionized, electrically charged gas that fills interplanetary and interstellar space alike, sometimes called the fourth state of matter because it behaves so differently from ordinary solids, liquids, and gases. Unlike some of the Voyager's other instruments, which detect magnetic fields or energetic particles indirectly, the Plasma Science instrument was built to directly sample the actual solar wind and interstellar plasma flowing past the spacecraft, measuring its density, temperature, and velocity in real time as the spacecraft physically moved through it, essentially acting like a direct physical sensor dipped straight into the surrounding environment rather than inferring conditions from a distance. It was, in a very real sense, one of the most direct, unambiguous tools either spacecraft carried for actually confirming what kind of environment surrounded it at any given moment, and its data has been fundamental to understanding the solar wind's behavior for nearly the entire duration of both missions. Sometime in the early 1980s, not long after Voyager 1 completed its planetary flybys of Jupiter and Saturn, its Plasma Science instrument stopped returning usable data. NASA has never pinpointed an exact cause with full certainty, but the leading explanation involves a damaged component within the instrument's electronics, likely degraded by the cumulative effects of decades of exposure to the harsh radiation environment of deep space, an environment nobody fully understood when the instrument was originally designed back in the early 1970s. Whatever the precise cause, the practical result was straightforward and, for scientists studying the spacecraft's eventual departure from the solar system decades later, genuinely frustrating. When Voyager 1 finally approached and then crossed the heliopause in August of 2012, the actual physical boundary separating our solar system's protective bubble from true interstellar space, its Plasma Science instrument had already been silent for roughly 3 decades, meaning the single most direct tool for confirming that historic moment had been unavailable for longer than many of the scientists eventually studying the crossing had even been working in the field. That absence forced scientists into a genuinely clever, but fundamentally indirect, workaround. Rather than reading a clean, direct plasma measurement confirming the crossing, researchers had to rely on a separate instrument, the plasma wave subsystem, which detects oscillations in the surrounding plasma rather than measuring its properties directly. In April of 2013, that instrument picked up plasma oscillations triggered by a solar eruption that had reached Voyager 1's location months earlier. And by analyzing the pitch and frequency of those oscillations, scientists were able to calculate the density of the surrounding plasma, and from that density, infer that Voyager 1 had indeed already crossed into interstellar space. It worked, and it stands as a genuine testament to how resourceful mission scientists can be when a primary instrument fails, essentially turning an entirely different piece of hardware into an improvised substitute for the one that had gone silent decades earlier. But it was fundamentally reconstructive, an educated deduction made well after the fact, rather than a direct, real-time observation of the crossing as it actually happened. NASA didn't even announce the crossing until September of 2013, more than a year after it had actually occurred, precisely because of how much careful, indirect analysis was required to confirm it with confidence. Voyager 2 didn't have that problem. Its Plasma Science instrument remained fully functional, still returning clean, direct data all the way through the spacecraft's own crossing into interstellar space on November 5th, 2018. For the first time in the history of either mission, scientists had a genuine, direct, real-time measurement of exactly what happens as a spacecraft physically passes through the true boundary of our solar system, rather than reconstructing that moment secondhand from an entirely different instrument's indirect readings. Engineers and scientists monitoring the spacecraft's data downlink didn't have to wait months for careful, painstaking analysis before they could say with confidence that the crossing had occurred. The plasma instrument's readings spoke for themselves, clearly and immediately. What that direct measurement revealed was immediately and genuinely informative. John Richardson, a principal research scientist at MIT who has led the plasma science investigation for the Voyager mission, described the data in strikingly direct terms once Voyager 2's instrument confirmed the crossing. The plasma density, he explained, jumped sharply by a factor of more than 20. Essentially, the moment the spacecraft crossed the heliopause, exactly matching what scientists had theoretically predicted the transition should look like, but had never actually been able to directly confirm using a live, functioning plasma sensor. That single direct measurement did something Voyager 1's indirect reconstruction never could. It gave researchers immediate, unambiguous confirmation of the crossing, in real time, rather than requiring months of after-the-fact analysis just to establish that the event had already happened, transforming what had previously been a slow, deductive process into something closer to simply reading a clear, direct answer straight off an instrument's dial. But the value of Voyager 2's working plasma instrument extended well beyond simply confirming the crossing itself. Because the instrument kept functioning after the crossing too, it let scientists do something they had never been able to do before at all: directly monitor the actual physical properties of interstellar plasma on an ongoing, ordinary basis, rather than relying entirely on indirect, event-triggered measurements, the way researchers had been forced to with Voyager 1. In November of 2019, this direct plasma data became the centerpiece of 5 separate papers published together in the peer-reviewed journal Nature Astronomy, each one covering findings from one of Voyager 2's still-functioning instruments, a magnetometer, 2 separate particle detectors, and 2 plasma-focused instruments working in tandem, painting the most detailed combined picture yet assembled of what conditions genuinely exist at, and beyond, the edge of our solar system. That data confirmed something scientists had predicted, and something that genuinely surprised them in roughly equal measure. As expected, interstellar plasma turned out to be considerably denser and noticeably colder than the plasma found within the heliosphere, exactly the kind of clean confirmation that gives researchers confidence in the broader picture their models had already been suggesting. But Voyager 2's direct measurements also revealed that the actual transition between the heliosphere and interstellar space was considerably sharper and more clearly defined than many scientists had originally expected. Closer to a genuine boundary than a slow, gradual blending between 2 environments, a detail no amount of indirect reconstruction from Voyager 1's older data alone could have ever confidently established. Researchers involved in the analysis suggested this sharpness implied the heliosphere's overall shape likely resembles something like a blunt, rounded bullet, rounded and compact on the leading edge, facing the direction of our solar system's motion through the galaxy, rather than the smooth, simple sphere. Many earlier, simplified models had assumed an image made possible specifically because Voyager 2's plasma instrument could measure the actual physical transition directly, rather than scientists having to infer its shape indirectly from scattered second-hand evidence the way they'd been limited to with Voyager 1 alone. There's a broader, genuinely important scientific principle buried inside this entire story, one that goes beyond the specific technical details of either spacecraft's instruments. Having 2 independent data points, gathered using working instruments at 2 different locations along the same boundary, separated by 6 years and by a considerable physical distance, gave scientists something a single spacecraft's data, however carefully analyzed, simply could never provide on its own, genuine confirmation that what they were observing reflected a real, consistent property of the heliopause itself, rather than some unusual, localized quirk specific to wherever Voyager 1 happened to cross. This is a foundational principle in nearly every branch of experimental science, that a single measurement, no matter how carefully collected, always carries some risk of reflecting a one-off anomaly rather than a genuine underlying pattern, and that real confidence only comes from independent replication. When Voyager 2's direct plasma measurements lined up with and meaningfully expanded upon the indirect conclusions scientists had already drawn from Voyager 1's data years earlier, it transformed an educated, carefully reconstructed inference into something considerably closer to genuine, confirmed scientific certainty. Exactly the kind of independent verification that separates a solid, trustworthy scientific conclusion from an interesting but ultimately unconfirmed hypothesis. This distinction matters enormously for one specific, deeply significant finding that came directly out of Voyager 2's working plasma instrument, one that connects directly to questions about life and safety here on Earth. Using Voyager 2's direct measurements of both solar and galactic cosmic ray particle flux, taken continuously as the spacecraft crossed the heliopause, scientists were able to confirm, with a level of confidence, Voyager 1's indirect data alone could never provide, that the heliosphere genuinely does block the majority of dangerous galactic cosmic radiation from ever reaching the inner solar system. That protective effect isn't just an abstract academic curiosity. It's directly relevant to any serious future planning around long-duration human spaceflight beyond our solar system, since understanding precisely how, and how reliably, that shielding actually functions depends on having real, direct, trustworthy measurements from right at the boundary where that protection is actually happening. Exactly the kind of data only a genuinely functioning instrument, still working after decades in deep space, could ever provide. Bill Kurth, a space physicist at the University of Iowa who has worked on the Voyager mission since the 1970s, has described the overall significance of having two independent crossings, studied through two very differently functioning sets of instruments, in terms that capture just how valuable this redundancy turned out to be. Rather than a single, isolated data point that later researchers would always have to treat with a degree of caution, Voyager 2's still-functioning plasma instrument transformed the entire heliopause crossing from an educated inference into something scientists could actually observe directly, compare against an independent second measurement, and build genuinely confident, well-supported conclusions on top of. So here's what I actually want you to take away from all of this. Voyager 1 will always hold the historic distinction of being the first human-made object to ever leave the solar system, a genuinely remarkable achievement that nothing can take away. But it was Voyager 2, arriving 6 years later, carrying a single working instrument its own twin had lost decades earlier, that actually let scientists watch that crossing happen in real time, directly, for the first and only time in human history. That difference, one functioning plasma sensor, changed an educated guess into confirmed direct scientific fact. And it gave researchers a genuine ongoing window into interstellar plasma that continues feeding new discoveries to this day. All because one specific piece of 1970s hardware simply refused to fail the way its identical twins had. There's a genuinely humbling lesson buried in this story, too, one that extends well beyond the Voyager mission itself. Space exploration rarely unfolds exactly according to plan, and the difference between a well-documented scientific triumph and a frustrating gap in our knowledge sometimes comes down to nothing more dramatic than which specific piece of nearly identical hardware happened to keep working a few decades longer than its twin. Mission planners can prepare for that kind of uncertainty, build in redundancy where they can, and train scientists to improvise resourceful workarounds when something inevitably fails, but they can never fully control it. Voyager 2's intact plasma instrument wasn't the result of some deliberate late design improvement. It was, as far as anyone has ever confirmed, simply a spacecraft that got lucky in exactly the one place where luck mattered most for this specific piece of scientific history. If you want to know what else Voyager 2's still-working plasma instrument picks up as it continues drifting deeper into interstellar space, subscribe and turn on notifications, because this instrument remains active right now, still gathering exactly the kind of direct measurements no other spacecraft in history has ever been able to provide. And drop a comment telling me whether you think Voyager 1's failed plasma instrument was simply bad luck, or whether you think Voyager 2 quietly benefited from lessons learned during its twin's earlier construction. Because honestly, after everything these two nearly identical machines have shown us, I think the real answer is more interesting than either explanation alone.